All right, we're going to move on to talk about practice problems. And here we're primarily going to be looking at problems related to the structured singular value. It's difficult to understand the thing in general, so we're going to look at it in some specific concrete examples. All right, so in this case, I have this matrix, 1, 2, 3, 4, obviously a contrived example. And this is my uncertainty set. My uncertainty has these two elements being uncertain. Okay, so we're basically looking at our uncertainty set being 2 by 2 matrices of this form for some values delta 1 and delta 2. If I remember, I'm looking for values where I minus A delta has determinant equal to 0. So I form I minus A delta. That's what this is. And when I take the determinant, this is what I get. I set that equal to 0. And so in this case, I'm going to solve for delta 1 from this expression. So delta 1 is actually this quantity. And so notice now I can write my uncertainty in general in this form, which only involves delta 2. So for any value of delta 2, this matrix will make this determinant equal 0. All right. So I've in the process eliminated one of the unknowns. I now have still one more unknown. So this is the form I have. And I now want to compute the singular values of delta. So delta times delta transpose gives me this expression. And again, so that's for delta 1. I'm going to substitute in what delta 1 is in terms of delta 2, and I get this expression. Okay, and notice this is a diagonal matrix, and since it's a diagonal matrix, the singular values are along the diagonal. So this is a self-adjoint matrix. Actually, it's a positive semi-definite matrix, and so the singular values for a diagonal positive definite matrix are along the diagonal. So this is the largest singular value, and it's a function of delta 2. And so if so the largest singular value squared actually is that quantity, which I can complete the squares. And so if we minimize the maximum singular value with respect to delta 2, I can see that I need delta 2 is equal to 1/5. And if I choose that, then the norm of capital delta, which is the largest singular value, is 1/2 root 5. It's the value that I get when I make this 0. Okay, and so that's the norm of the uncertainty. The mu is 1 over that, and so we get 2 root 5 as our structured singular value for this particular matrix. So in this case, that's what we get. Now, if we assume that there was no structure in that matrix, and I go through and do the singular value decomposition, this is what I get. So you can see it's pretty complicated looking, because in general, when you have only under special cases do you get matrices with singular values that look reasonable. This is pretty common to have square roots of square roots kinds of things. So these are our U and our V matrices. So these are singular values. So notice this is a smaller singular value than this is. They're still both positive. Okay, and so again, the smallest perturbation in this case, multiplicative perturbation, is given by this expression, which comes out to be this. And the norm of that is 1 over sigma 1, which is this quantity, which is this number. When we go through and compute the largest 1 over the largest singular value, the structured singular value, we get this number, which is this. And so we have that situation. Okay, so again, this number is larger than that number, which is what we were expecting. All right, so that's the first example of going through and computing the structured singular value for a particular structure. Now let's take the same matrix, change our structure. So this is our structure. It's a diagonal matrix with 2 different elements along the diagonal. We compute the determinant of I minus A delta. We get this. This is the determinant. Set it equal to 0. Again, I solve for delta 1 in terms of delta 2. This is what I get when I solve this equation for delta 1. Okay, so now my uncertainty is written only in terms of delta 2. I could do it the other way around. I just chose to solve delta 1 for in terms of delta 2. I could have done delta 2 in terms of delta 1 just as easily. And so this is what we get. This delta, when I multiply by a, gives I minus a delta equals 0. Determinant. Okay. So this, again, this is a diagonal matrix, and as a diagonal matrix, its singular values are the absolute values of the diagonal elements. Okay. So these are our two singular values, and it's hard to say just by looking at them which one is the larger of the two. And so, and when does the minimum of the maximum of these two occur? Okay, so both of these are functions of delta, but I can't tell when the minimum, which one is larger than the other. And in general, one will be larger than the other, and they may switch places. So these are both functions of delta 2. I'm going to plot them as functions of delta 2. So here's this guy here looks like that. This guy here is like this. Okay, and so the minimum of the maximums occurs where these two guys meet, right at that point. And pretty much you'll always get something like that happen. That is, you'll have two singular values, and wherever they're actually equal to each other, that's the point that you're looking for. So in this case, the minimum of the maximum occurs when these two values are actually equal to each other. So when delta 2 is positive, this quantity ends up being positive. So I can drop the absolute value signs. And again, delta 2 is positive, so I can drop the absolute value signs. So these two are equal to each other. I can solve for delta 2 from this expression, and I get this. Okay, I get a quadratic. Okay, and only one of the two roots is going to be positive. I'm sorry, I'm looking for the minimum of the maximum. So this is going to give me the minimum of the roots. So this is the number I get. So that's the value that I'm looking for. Okay, and so for this problem, mu is 1 over that, which is this number. If we take this matrix and compute the spectral radius, this is what we get. If we take this matrix and compute the largest singular value, this is what we get. So notice we have, in fact, the set of inequalities holding. These actually happen to be equal to each other, and they're both less than or equal to this. So notice in this case, the largest singular value and the spectral radius are actually pretty close to one another. So it's unusual to have them so close, but in this case it happens. And the structured singular value is in between the two. So we have that. All right. Here's our matrix. And our uncertainty set we're going to change yet again. In this case, we're going to set it so that we just have one value, the same value in both cases. And so we compute 1 minus I minus a delta determinant. This is what we get. We solve for delta, and this is what we get. So notice in this case, we have an exact formula for delta. And these are reciprocals of one another. And so this is, in this case, our structured singular value is our spectral radius, and it's equal to that quantity. So we have this simple case. So that's example 3. Example 4. Here's my matrix. So it's very similar to what we had before, but instead of having 4 here, I have 6, which makes this matrix into a dyad. Okay, and here I'm going to have a diagonal uncertainty matrix. So again, 1 minus a delta we can show is equal to this, which boils down to this. Solving that for setting it equal to 0 and solving for delta 1, I get this, and so this is my uncertainty set. Okay, and so I have these two singular values, or the absolute value of these are the singular values. And again, they're both functions of delta 2, but it's not obvious by looking at these two which is less than the other, and how do you minimize the maximum, and so forth. So again, in this case, this is straightforward enough. I can actually plot them. Okay, and so these are the plots. So this is delta 2 absolute value. This is delta 1 absolute value, which is written in terms of delta 2. And so we have this expression. So I just plotted these two absolute values. And again, the minimum of the maximum, so remember these are two values. So for example here, this is smaller than this. So this is the minimum of the two. Okay, but I need the maximum. I need the maximum singular value. So this is the maximum. This is greater than this. So this is the max. Here, this is the maximum. So you can see the maximums change places. And so the minimum of the maximum, so the overall maximum, if I were just to plot the overall maximum, it would be this guy down to here, and then it would be this guy over to here, and then be this guy. That would be the maximum singular value as a function of delta 2. Okay, the minimum of the maximum occurs right at that point there. And so in that case, both delta and this quantity are equal to each other. So notice that in this case, this quantity is actually, the negative of this quantity is actually what the absolute value is. And so that's why I have this as opposed to 6 delta minus 1. I have minus 6 delta plus 1. So it's when this is the case. So this would have been positive on this side of that breakpoint. Okay, on that side of the breakpoint, it's negative. So that's that point there occurs on the negative side of this V inequality. All right, so this is the equation I have. I solve this for delta 2. I get 1/7, and so the norm of the uncertainty is 1/7, and so the structured singular value is 1 over that, which is 7. Using the formula that we had, we can go through and show, in this case, this expression, which is 7, so it confirms the result. So we've gone through now and we've done 4 examples of computing the structured singular value for various cases. And this then concludes our presentation on the structured singular value. We'll come back later and we'll use this guy because it actually is an important quantity, even if it is a complicated one to have to work with.